The 28th of January 1986 was a year when NASA was truly soaring. With the Mercury mission, they sent the first American into space, giving a fitting response to the Soviets. The Gemini missions marked the first time in history an astronaut survived in the vacuum of space. And the 14 different Apollo missions, 6 of which landed on the moon, transported a total of 24 astronauts. Among them, 12 walked on the moon, a celestial body once deemed unreachable. NASA also placed America's first space station into Earth's orbit with the Skylab mission, which would later pave the way for the International Space Station. The Viking program achieved the first successful landing of a spacecraft on Mars, and the Voyager program sent the first vehicles destined to leave our solar system. These continuous successes, marking a definitive win in the space race against the Soviets, inspired countless generations. However, just 73 seconds into a launch, a tragic incident led to the death of 14 astronauts. This series of errors revealed a profound story, not just relevant to space research, but also offering significant lessons for our own lives. Despite every NASA achievement serving as a remarkable advertisement and source of inspiration, the realization that the Soviets could no longer catch up in space led to a rapid decrease in NASA's budget. In 1966, at the peak of the space race, NASA's budget was only 4% of the government's total. By the 80s, this had dropped to 1%, and by 2023, it was projected to decline even further. Facing financial pressures in the 80s, NASA was forced to innovate for self-sufficiency, or risk shutting down their space programs. This led to the birth of the Space Shuttle program, known in Turkish as Uzay. This program was designed to transport astronauts and experiments for other institutions into space, generating income to fund other projects. NASA proposed an experimental approach never tried before. Until then, rockets sent to space weren't reusable, except for the crew capsule. NASA pioneered the idea of a reusable rocket, a concept familiar today through companies like SpaceX. Space shuttles were unique in their ability to glide back to Earth like an airplane and be reused for multiple missions. These shuttles were transported to space attached to a massive orange tank, the main fuel reservoir containing liquid hydrogen and oxygen. After reaching space, this tank would detach and disintegrate upon re-entering the Earth's atmosphere. The shuttle's main engines and a pair of solid rocket boosters, which were detached post-launch and later recovered for reuse, were instrumental in its initial ascent. Without a comprehensive station like the International Space Station at the time, these orbiters would orbit Earth for hours or even days, as in the case of the STS-80 mission in 1996, which lasted nearly 18 days. The Space Shuttle program was responsible for deploying renowned observatories and satellites like the Hubble Space Telescope, Chandra X-ray Observatory, and the Magellan spacecraft. Most of the International Space Station's components were also transported by the shuttles, along with astronauts for maintenance and research missions. These shuttles didn't just deploy satellites and telescopes, they were pivotal in testing new equipment, flight techniques, refreshing the crew of the International Space Station, and conducting Earth observation missions. Overall, the Space Shuttle program was a monumental step in space exploration, demonstrating the possibilities and challenges of reusable spacecraft and contributing significantly to our understanding of space. In the early stages, everything about NASA's Space Shuttle program seemed flawless. The shuttles were launching one after another, carrying experiments from both military and civilian research organizations into space. Despite these advancements, the Space Shuttle program was exceedingly expensive. Analyses showed that to be profitable, the program needed to launch at least 60 times a year, which means a launch every 6 days. However, by 1986, NASA had never managed more than 9 flights in a single year. This situation put immense financial pressure on NASA's management, which in turn was passed down to the engineers. Engineers were tasked with rigorously inspecting returned shuttle parts, replacing worn components, and repairing any damages. As you can imagine, shuttles going to space, spending days in orbit, and then re-entering Earth's atmosphere under extreme temperatures, took a toll on these mechanical devices. I once visited a museum where the Endeavour space shuttle, one of the last shuttles, was displayed. In my video, you can see the immense size of these shuttles. Considering the issues that could arise within the shuttle's internal parts and rockets, the repair and improvement tasks for engineers were anything but simple. Now let's delve into the Challenger disaster's root cause in 1986. Engineers at Morton Thiokol, a contractor working with NASA, noticed a design flaw in the reusable rockets. Rockets aren't made from a single piece. They consist of several segments connected by O-ring seals, as the name suggests, shaped like an O. These seals prevent the rocket's fuel from leaking at the connection points. However, especially during cold weather launches, the engineers discovered that the primary O-ring would fail to seal properly, allowing fuel to leak. But fortunately, the secondary O-ring would stop the leakage. This was an unacceptable risk for the Space Shuttle missions. An engineer at Morton Thiokol immediately alerted NASA, and thankfully, his concerns were taken seriously. Initial improvements seemed to work, temporarily stopping the fuel leaks. However, subsequent flights showed that fuel could still bypass the first O-ring but was contained by the second. Despite repeated warnings from the engineers, NASA's response was dismissive. Eventually, NASA, under the influence of successive achievements and unchecked capitalist impulses, chose to alter flight rules, declaring that minimal damage like this was acceptable for flight. This decision was a precursor to a terrible disaster about to unfold in front of millions. Now let's return to the 28th of January, 1986. The Challenger disaster. Confidence was so high that no one anticipated a catastrophe. NASA had decided to send a civilian, a female high school teacher, into space for the first time. Chosen from thousands of applicants, Krista McAuliffe was to be broadcast live to thousands of schools. The crew also included a diverse range of professionals: Commander Francis Scobie, an experienced astronaut who had flown with Challenger in 1984, pilot Michael J. Smith, making his first spaceflight, and Air Force pilot Ellison Onizuka, ready for his second astronaut mission. Gregory Jarvis, another first-timer, was on board to conduct experiments for Hughes Aircraft Company. They were a fearless team, unaware of the tragedy that was about to strike. They boarded the Challenger and strapped in. But there was a problem. Temperatures the night before the launch had plummeted to minus 7.5 degrees Celsius, freezing everything on the launch pad. Although temperatures rose to 22.5 degrees on launch day, it was still 10 degrees colder than any previous launch. NASA was venturing into unknown territory. Despite repeated postponements due to bad weather, technical errors, and planning conflicts, NASA, under immense public scrutiny and with many students watching, was reluctant to delay again. During an emergency teleconference the night before the launch between Morton Thiokol and NASA, concerns were raised about the extreme cold. An engineer strongly advised against launching unless temperatures exceeded 12.2 degrees Celsius. Stay tuned to learn what happened next in this incredible tale of human endeavor, ambition, and the lessons learned from one of history's most significant space tragedies. If the concerns raised by engineers were heeded, the Challenger launch might have been postponed until April. NASA, pressured to maintain a launch every week, faced a dilemma. Either heed the warnings of engineers advocating for a delay, or proceed under financial and political pressures. Engineers at Morton Thiokol, after repeatedly reviewing their data, couldn't find a reason to change their initial recommendation against the launch. Alan McDonald, the head engineer for the Space Shuttle's solid rocket motor project, stood by the right decision and refused to approve the launch. However, NASA, determined to proceed, took the decision out of the engineers' hands and left it to the executives of Morton Thiokol. Unsurprisingly, the company executives, driven by shareholder interests, signed off on the launch approval within 30 minutes. Despite the engineers' objections, the Challenger was set to launch. Everything up to the launch went routinely. The countdown proceeded, and the rocket ignited with a terrifying roar. But there was a problem, visible even to the naked eye. Those black smoke plumes? They were from the extreme hot gases leaking from the O-rings at the base of the right rocket booster. A clear sign of impending disaster. The shuttle ascended smoothly for a minute, performing all necessary maneuvers. There was slightly more wind shear than expected, but nothing the shuttle's control systems couldn't handle. The thrust was reduced and then increased as planned. Yet, unbeknownst to anyone, the leak was worsening, causing the right and left rocket boosters to fire unevenly. Fortunately, the flight control system compensated automatically, but under intense vibrations and extreme fuel temperatures, the O-rings continued to deteriorate, allowing more hydrogen to escape. A minute into the flight, cameras captured a flash at the site of the leak, followed by a fire. This fire grew within half a second, compromising the structural integrity of the rocket. In the milliseconds before the final explosion, the oxygen tank began leaking, followed by a blast between the external tank and the shuttle. The Challenger exploded in full view of millions. NASA and the 7 lives entrusted to it became victims of hurried decisions. The Rogers Commission, how NASA addressed the Challenger mistakes. Following the Challenger disaster, a 13-member Rogers Commission, including notable figures like Neil Armstrong, physicist Richard Feynman, and astronaut Sally Ride, was formed. They unearthed all the events I've described in full detail. A harrowing finding from the Commission's report suggested that the astronauts might have survived the initial explosion, only to perish from impact or drowning when hitting the ocean at over 350 kilometers per h. However, the exact cause of death remains unknown, as telemetry and communication were cut off after the explosion. NASA took several measures to ensure such a tragedy never happened again. Solid fuel boosters were redesigned, and new O-ring designs and heaters were introduced, eliminating the risk of similar problems in cold weather launches. Emergency protocols were revamped, equipment updated, and a safety office was established to oversee NASA. The Teacher in Space program was canceled, but in 1998, it was revived as the Educator Astronaut program. Barbara Morgan, Krista McAuliffe's backup, became the first teacher in space on the Endeavour mission in 2007. It took 2 years for NASA to resume Space Shuttle flights, but they deserve credit for not hastily scrapping such significant missions and instead implementing necessary safety measures. From 1986 to 2003, NASA successfully conducted 87 more Space Shuttle missions. Each flight represented a victory, too vast to fit into this video. You might wonder why I stopped at 2003. That's because on January 16, 2003, the Columbia, NASA's first space shuttle, embarked on its 28th mission, setting the stage for yet another series of complacency and management errors leading to disaster. This time, the spotlight was on the heat shields of the space shuttle, one of the revolutionary innovations of that era. As seen in my other video where I went under the Endeavour, these shields weren't manufactured as a single piece. They consisted of hundreds of small tiles covering the entire underside of the shuttle, including the wing undersides. However, during Columbia's launch, a piece of foam insulation from the orange external tank broke off and struck these heat shields on the shuttle's left wing with significant force. Such foam shedding had been observed in previous launches, but what went unnoticed this time was the unusually large size of the broken piece. Tragically, the extent of damage this caused to Columbia was not immediately apparent. Still, the shuttle successfully reached Earth's orbit with its 7-member crew. The horrific hours for NASA were yet to come. Engineers on the ground, while routinely reviewing launch footage, only noticed the collision on the mission's second day. NASA, United Space Alliance, and Boeing promptly formed an engineering committee. Their simulations indicated not only potential damage to the heat shields, but also to the aluminum frame they protected. This damage could prove catastrophic during the shuttle's re-entry into Earth's atmosphere due to extreme heat. The committee suggested using the Defense Department's observation satellites to photograph the wing from space for a closer inspection. However, this would require Columbia to alter its position, interrupting ongoing experiments. Linda Ham, the mission operations manager at the time, rejected this request. She believed that the Defense Department's camera resolution would not be sensitive enough to detect such damage. Consequently, Mission Control chose to disregard the damage. On January 23, 2003, Commander Rick Husband and pilot William McCool were informed of the incident, but reassured that there was nothing to worry about. As a side note, pilot William McCool was the son of one of my wife's professors at Texas Tech University and an alumnus of Texas Tech's Mechanical Engineering Department, where I completed my doctorate. Columbia was his first spaceflight. The crew also included experienced payload commander Michael Anderson, Israel's first astronaut Ilan Ramon, Indian-American astronaut Kalpana Chawla, and U.S. Navy captains Laurel Clark and David Brown. Under these dire circumstances, on February 1, 2003, the crew began re-entry into Earth's atmosphere from 120 kilometers above. Immediately, the excessively high temperatures began rapidly melting the already damaged aluminum beneath the heat shields. About 4.5 minutes into re-entry, sensors on the left wing reported excessive strain. The flight control system automatically compensated for this, delaying the detection of the problem. Soon after, warnings of excessive heat on the left wing were received. 9 minutes into re-entry, Columbia passed over the California coast at Mach 23, approximately 28,400 kilometers per h, at an altitude of about 71 kilometers. Just 30 seconds later, observers in New Mexico captured footage of a significant debris trail following the left wing. The shuttle continued to shed debris over Utah, Arizona, New Mexico, and Texas. A minute and a half after that photo was taken, all communication with Columbia was lost. Husband's last words were, "Roger, but," while the shuttle was still traveling over Mach 15 and began to spin, subjecting the crew to up to 3 Gs of acceleration. Analysis of the mission recordings suggests that either Husband or McCool switched to manual control about 30 seconds after communication was lost, indicating they were still alive at that point. However, only 15 seconds later, the shuttle disintegrated completely. The crew experienced a traumatic death, not primarily due to the forces during re-entry, but rather due to the rapid decompression when the cabin broke apart. Post-mortem examinations revealed that some astronauts' helmets were not fully secured, and one astronaut's helmet wasn't on at all, suggesting the decompression happened too quickly for any response. Additionally, their shoulder straps failed to restrain them effectively, causing severe injuries as their heads repeatedly struck the helmet's interiors. The astronauts likely also suffered significant thermal trauma as hot gases from the disintegrating shuttle entered the cabin. For example, one astronaut's clothing was completely torn away due to exposure to the external winds following the breakup, and molten metal droplets were found on some of the bodies. Ultimately, the shuttle crashed in East Texas, with only bacteria and the experimentally transported Caenorhabditis elegans worms surviving the catastrophic impact. Following the Columbia disaster, NASA initiated a series of investigations, uncovering a distressing truth. Studies revealed that extending Columbia's mission to 30 days could have allowed for a rescue mission using the Atlantis shuttle, which was scheduled for a March launch. This could have potentially saved all the astronauts. Again, a fixation on success and complacency in the face of repeated achievements had led to a deadly outcome for NASA. Subsequent processes were revamped, and although flights resumed in 2005, the Space Shuttle program concluded in 2011 after 22 more missions. At this point, NASA became reliant on Russian launch vehicles for years until private enterprises like SpaceX emerged, enabling astronaut launches from American soil once more. At the time of making this video, the first Turkish astronaut, Air Force Major Alper Gezerovci, is set to be launched into space using SpaceX's Crew Dragon module as part of the IOM Space Company's A3 mission. I'm not telling this story to praise or criticize NASA. The Space Shuttle program, over 30 years with 5 shuttles, successfully completed 133 of its 135 missions, carrying over 350 people from a wide range of backgrounds into space. These astronauts spent a total of 1,300 days in orbit, traveling 800.72 million kilometers, making incredible contributions to humanity. Notably, the program enabled the Hubble Space Telescope to be repaired 5 times, extending its operational life significantly. My purpose here is not to point fingers, but to sound a cautionary note. As a society, we need to learn realistic and lasting lessons from our mistakes. It's clear that institutions and companies should be rigorously and independently scrutinized, regardless of whether times are good or bad. Overconfidence inevitably leads to grave errors, big or small. Fields like space exploration at the cutting edge of science do not tolerate even the slightest indiscipline, negligence, or arrogance. The uncertainties and risks in such endeavors are too great to allow for complacency in decision-making roles. Never forget, no achievement is so grand as to legitimize a relaxed approach and responsibilities that impact many lives. Until the next video, take care and goodbye.